chị Tú Đúc. Đồng chí, good morning everyone. So we are very pleased to introduce the first speaker of our last day of the workshop. He is Nguyễn Tất Thắng. He comes from Hanoi Institute of Mathematics of Vietnam. And the main research interest of Nguyễn Tất Thắng involves several topics in singularity theory, such as, for instance, the motivic minor fibers, the bifurcation sets of polynomial mappings, among others. And today he will talk about minor number of non-degenerate isolated complete intersection singularities. So please, Anh Thắng, you can start now.
Thank you very much. Thanks to you. Thank you for the introduction. Is everybody hearing me? Can you hear me? Hello?
Yes.
Okay. Okay, firstly, I would like to thank the organizer for inviting me to give a talk in this night's workshop. It is my great honor to give a talk in the plenary session. I am also very happy to give a talk in the occasion of the 60th birthday of Professor Osamu Saiki. So I would like to say congratulations to Professor Osamu Saiki for the 60th birthday, and I wish you with good health and happiness. Now let me start my presentation. Today I'm going to talk about the minor number of non-degenerate isolated complete intersection singularities. In the first part, I will explain the setting of hypersurface singularities. As all of you know, for each analytic function germ f from Cn to C with an isolated singular point 0, say 0, then there is a notion, namely the minor number. So the minor number of f at the origin is defined to be the dimension of the quotient of the ring of germs of analytic function at the origin and over if, which is the idea of the idea generated by all partial derivative of f. So the minor number is denoted by mu of f. So this is the minor number of f at the origin. So this number is important because it measures the multiplicity of the singular point. It also have many information of the topology of the fiber of f. So you can see in this slide. So it is known that for any f, then it defines a locally trivial fibration at the origin, near the origin. More precisely, if we fix epsilon to be small enough, small meaning that the zero set of f intersects transversal to any smaller sphere with a smaller radius, smaller than epsilon. So if we fix any small number epsilon, then for any small number eta, we will have a locally trivial fibration of f on the punctual disk d eta intersect with the bore d epsilon. So we have the first the second line. We have, in this second line we have locally trivial fibration. I'm not sure whether you see this mouse. Do you see the mouse of my screen? I don't know. Can I use mouse here? Okay, so this fibration we call it minor fibration. It is proved by Minor and Lê Trung Trang. And the fiber of this fibration is denoted by F0F, and we call it the minor fiber of F at the origin. And there is a relation between the minor number with this minor fiber. It is proved by Minor that here in this case, I always assume that F have isolated singularity at the origin. And then in that case, the minor fiber has a homotopy of the bouquet of stress of dimension n minus one. The number of stress here is exactly the minor number of F. And it follows from this fact that the minor number of F equal to the n minus one Betti number of the minor fiber. Because of this reason, the minor number is very important in the study of the singularity. Then, it is a question that how to compute the minor number. So this is the notion of the minor number, and there are many studies about the minor number. In the case of non-degenerate hypersurface singularity, there is a famous formula proved by Kuznetsov. So, firstly, I need some notation. Here, for each analytic function germ f, assume f have this representation like the sum of the monomials. Then the Newton diagram of f is defined to be the convex of this set. This is the set of the exponent appear in the function f, is the expansion of f, and the Newton boundary gamma of f is a union of the compact faces of the Newton diagram. And we say that the function is Kuznetsov non-degenerate if for any compact phase gamma of the Newton diagram, then the first function, the function which is defined to be the sum of the terms in f, whose exponent belong to the first gamma, has no critical point in C star to the n. So this is notion of the Kuznetsov non-degeneracy, and this definition is open. It's open in the set of all functions with the same Newton diagram. Another notion called Newton number is defined as follows. So for each delta to be a convenient Pareto in Rn, then the Newton number of delta is defined by this formula, where this V is a volume of the volume of delta, and Vi is a volume of the intersection of delta with a coordinate hyperplane, and we have other Vij, etc. So we have this notion of a Newton number of a convenient Pareto, and of course this number is computed can be computed combinatorically, and it is proved by Kuznetsov that if f with a function germ f is non-degenerate and convenient, then the minor number of f at the origin is equal to the Newton number of the Newton diagram of f. Actually, this is not the Newton diagram f. It should be the complement of the the complement of the Newton diagram of F. Yeah. So this is the formula of the Kuznetsov for the minimum number of non-degenerate and convenient hypersurface function. And the aim of my talk is try to generalize this result for F to be a complete intersection. That is the aim of my talk. Now I will go through to introduce some notion in the setting of complete intersection. Here, let F be a germ of analytic mapping, such that the origin belongs to the zero set of F, and I assume that the zero set of F is a complete intersection with isolated singularity at the origin. So I assume that the origin is an isolated singularity of this zero set. And now I will define. I will introduce the notion of. I will introduce the minor vibration for F. So the minor vibration for analytic mapping is quite similar to the one of hypersurface function. So firstly, we need to fix some small ball at the origin. Say let epsilon be a small number such that any sphere with radius smaller than epsilon 0 intersects transversely with V. Yeah, so I assume that any smaller sphere intersect transversely to with the zero set of F. So this epsilon 0 will be fixed, and then I choose U to be small open neighborhood of the origin in the image, in the target in CP, such that we have this condition. So this condition means that any fiber of the point in U also intersects transversely to the sphere of the radius epsilon 0. So here I fix the sphere and I choose U to be small neighborhood of the 0 of the value 0 in the target, such that any nearby fiber intersects this sphere transversely. So this we can choose such U. Okay, and I denote by D of F the set of critical values of the function F of the mapping F restricting on to this union. So I consider the restriction of F to this small ball, and then I denote D of F to be the set of critical values of this function. Sometimes we call D of F the set of the discriminant set. Okay, with those notation, we also have this minor vibration, which is the restriction of F on the complement of D of F, of the inverse of D of F. So we have this math is locally trivial vibration. So this is because of the Erasmus theorem. We have this locally trivial vibration, and this vibration also is called minor vibration of F, the map F at the origin. And the minor fiber of F at the origin is defined to be the fiber of this vibration. It is denoted by also by F0 of F, and it is defined by this formula. It is the inverse. It is a fiber of f at any small value t, and intersect with the small ball. And it is similar to the case of hypersurface. That in this case we also have uh, the homotopy of the middle fiber like a bouquet of sphere. So it is proved by Ham that the middle fiber of F at the origin is have homotopy of the bouquet of sphere of the dimension m-1. Here n is the number of variables of F. And the problem is that how to know the number of the sphere here. And then we denote by mu F to be the n-1 Betty number of the minor fiber, which is exactly the number of the sphere in this bouquet of spheres, in this bouquet of sphere. And we call it the minor number of F at the origin. So in the case of complete intersection singularity, the minor number is defined in terms of the topological information. We don't have um, an algebraic formula for this minor number like in the hypersurface case. And our aim is to compute this minor number. Try to compute this minor number for some special case, like in the case of non-degenerate. Okay, now I will introduce the notion of Kovarsky non-degenerate. So for now, let gamma be a polyhedral in Rn, and for each non-zero vector q in Rn, we consider the function defined by q, the inner product defined by q. This function defined on gamma, and the minimum of the value, the minimum of the function defined by q on gamma is denoted by dq gamma, and I denote by gamma by delta q gamma to be the set of the point on gamma such that this function attain its minimal values. So delta q is exact is nothing else but the phase. It is the phase of this polyhedral with the direction whose orthogonal who q is one orthogonal vector. So this is one phase of gamma. And we say that so F here is a mapping from Cn to Cp, say Cn to Cp. And we say that this map F is Kovarsky non-degenerate if for any positive vector q we have this type. So this means the matrix of the own partial derivative of the phase function of F. So F delta is defined by exactly the phase function of each component of F, and we have a map, and then we take the Jacobian matrix. Then this is the rank of the Jacobian matrix. It required to be less than P. If the set of points whose the rank of this matrix less than Q, this Q is a number. Q is a dimension of the target space of F. Yeah, so we require that this set intersect with the zero set of F delta should be contained in the hyperplane coordinate. Yeah, so this is the notion of Khovansky non-degeneracy. When P equal to 1, and this notion coincides with the notion of Kuznetsenko non-degeneracy. Okay, now I go through to my work. In my work, I mainly study the family of analytic mapping. So say F, the variable is T and H. T is one variable, and H belongs to Cn. So I assume that F is analytic in this sense. And so what I want to study is that I want to compare the minor fiber or the minor vibration of this family. So this is a family of function from Cn to Cp. When we fix T, we consider T to be a parameter. Then we have a family of of analytic mapping from Cn to Cp. And we want to study to compare the minor fiber or the minor vibration of this family to each other. Then in order to do that, we try to find some fixed minor ball. So it also means so here we have epsilon 0. So maybe it's easier to see by if we see this slide. So here we have the minor vibration of the function on small ball with radius epsilon. So this epsilon, sometimes we call it the minor b. Sometimes we call b epsilon to be the minor sphere. And in order to study the minor vibration, sometimes we try to control or to know the minor sphere of F, and therefore we in the case of family, so for each t, the function for each t, the mapping F will have a minor sphere, and we want, in order to study the relation of the minor vibration of this family, we want one of the method is to compare the minor ball of each function. And then we have that's the reason why we have this definition. In this definition, we define the notion of uniform stable radius. So the uniform stable radius is a positive number epsilon 0 such that the sphere or the ball with radius epsilon 0 is the minor ball for all function ft. That is the meaning of this notion. So if epsilon 0 is a uniform stable radius, then for any t, the function ft will define a locally trivial vibration on the open ball with radius epsilon 0. That is one of the meaning of this notion. And this definition is defined by Musuoka. Okay, of course, it's not always the uniform stable radius of a family not always exists. But if it exists, then we have this fact. So assume that the family Ft have an uniform stable radius, and assume that for each t, the zero set of Ft is a complete intersection. Then the minor fibers of every Ft are diffeomorphic to each other. So this is one of the reasons why we want to study the uniform stable radius. Okay, so one of our main result is a following. So let F and G to be two genres of analytic mappings such that it satisfies these two conditions. The first condition is that F and G have the same Newton diagram. So this condition meaning that the Newton diagram of each component of F and G coincide. So because F and G are mappings, then F have the P components. Each component is a function, is an analytic function. Then the first condition means that the Newton diagram of each component of F and G coincides. And the second condition is that F, G are non-degenerate, are Kowalski non-degenerate, and the zero set of F and G are complete intersection with isolated singularity at the origin. So with these two conditions, then we can find a piecewise analytic family Ft of analytic maps such that it connects F and G, and the family have a uniform stable radius. Also, for each t, then the zero set of Ft is a complete intersection. So this is the main result in this talk. And remark that in this theorem, I do not require F and G to be convenient. In the case F and G are convenient, this result is proved by Musuoka by using toric modification. And this theorem, I proved this theorem for FG can be not convenient. Okay, I will explain the idea of the proof of this theorem later. But let me continue the talk. Is there any question or comment? Is there any question so far? If you have any question, please tell me. Because I know you are many people, but I am here alone, so like I speak only to me. Okay. Okay. So one of the corollary of this theorem is the following: if two germ F and G have satisfied these two conditions, then the minor fiber of F and G are diffeomorphic, or it also implies that the minor number of F at the origin equal to the minor number of G at the origin. So this notation is quite different to the one at the beginning. The difference is that I put 0 here. So 0 here, I want to say that this is the minor number of F at the origin. So this is the origin. And this fact, this is true because we know that when we have this uniform stable radius, then we can construct a diffeomorphism from the or more precisely, I should say that we can prove that the minor vibration of F and the minor vibration of G are isomorphic, and because of that, the minor fiber of F and the minor fiber of G are diffeomorphic, and then the Z minor number are equal. I also want to remark that in case F and G are convenient, so this fact is a corollary of a result by Professor Gaffney. So Professor Gaffney proves that if F is if the mapping F is convenient and Kowalski non-degenerate, then any small deformation of F deformed by the term above the Newton diagram, then the deformation is a Whitney singularity. Then we have this claim. So in case F, G are convenient, so this fact is known by the result of Professor Gaffney. Of course, in my result, I do not require F and G are convenient. Okay, I will use this theorem to study to compute the minor number of f. And this is an important fact. Because of this fact, in order to compute the minor number of f, we will deform f such that we can compute this number. So, okay, in order to introduce the formula of the minor number of non-degenerate complete intersection, I need the notion of mixed covolume and mixed Newton number. So this notion is introduced by Divya or Ozina, and I use his formula. Okay. Here, gamma plus is a convenient Newton polyhedron. Then the covolume of gamma plus is defined to be the volume of the complement of this set. And it is proved by Cavet and Kovarsky that the covolume of this Minkowski sum. So we have a family. This is the P. This is the correction of convenient polyhedron. So we have P convenient polyhedron, and we consider the Minkowski sum of this polyhedron, where T1 and TP are any real numbers. Then it is proved that the covolume of this Minkowski sum is a homogeneous polynomial of T1 to TP. So it can be expand can be written in this form. So this is the monomials. This is the monomials, and this is the coefficient. This is the coefficient. This is the coefficient of this polynomial. And this notation covolume of this family of polyhedron is exactly the coefficient of this polynomial. Yeah. And we will define that the mixed covolume of this family to be the coefficient in this formula. So on the right hand side we have a polynomial, and on the left hand side it is the covolume of this Minkowski sum, and on the right hand side we have the expansion of this polynomial, and the coefficient is denoted by this notation, and so it can be computed in terms of the left hand side, and this coefficient we call it the covolume, the mixed covolume of this family of the Newton polyhedron, and we denote by this notation the covolume of this family. So this is a notion of the mixed covolume. So it's quite complicated, but you can see that remember that mixed covolume of a family of the polyhedron is defined from the combinatoric information of the polyhedron, and it is a generalization of the mixed volume of one polyhedron. Okay, here in this slide I will define the mixed Newton number. The mixed Newton number is defined by Divya Ozina, and it is the notion for each family of convenient polyhedron. So let gamma 1 to gamma p plus to be convenient polyhedron in Rn. Then the mixed Newton number of this family of polyhedron is defined by this formula. So this is again also a complicated formula, but here the J is gamma 1 to gamma p is the sum of covolent, of the mixed covolent. So you can remember that, so the mixed Newton number is some number defined in terms of the combinatorial information of the Newton polyhedra, of the polyhedra. This is the formula for the mixed Newton number. It remarks that if p equal to 1, if p means we have only one polyhedron, then the mixed Newton number coincides with the usual Newton number defined by Kushner and co. So when p equal to 1, then we have the same number. Okay, I here in this slide I will recall the result of the formula of Bivia-Orsina. He proved that uh, in if the analytic mapping F is convenient and Newton non-degenerate, then the minimum number of F at the origin equal to the mixed Newton number, which is defined in the previous slide. So gamma 1, gamma plus 1 F1 and gamma plus Fp are the Newton polyhedra of the coordinate function of F. And here the notion I'm not going to define the notion of Newton non-degeneracy. So this is a kind of notion of Newton non-degeneracy. But we can see in this remark that so this notion is defined by Bivia-Orsina, and it is a generic notion. Generic means that if we fix the Newton polyhedron of all of the coordinate function here, then when we then the set of Newton non-degenerate mapping form an open set of the set of all mapping with the same Newton polyhedron. So that is the meaning of the generic notion. Generic, it is a genericity of the Newton non-degeneracy. But this notion is stronger than the notion of Kowalski non-degeneracy. This implication is proved by Bivia-Orsina that if the mapping F is Newton non-degeneracy, then it is Kowalski non-degeneracy. But the inverse is not true. The counterexample by Bivia-Orsina. I do not read it here, write it here, but it is written in the paper of Bivia-Orsina. So we have different notion of non-degeneracy. And we try to generalize this formula for the setting of Kowalski non-degeneracy, and I also want to remove the condition convenient here. Okay, so this is our result that assume F to be convenient and Kowalski non-degenerate, then we also have the same formula. And the proof is quite simple, that we use because the Newton non-degenerate is open, then we can find a mapping G with the same Newton polyhedra with F, but G is Newton non-degenerate. And again, because G is Newton non-degenerate, then it is also Kowalski non-degenerate. Now we have F and G are Kowalski non-degenerate convenient, and they have the same Newton polyhedra. Therefore, the minimum number are equal. This fact is proved in the corollary of theorem 1. in my talk, and then I apply the result, the formula of PVR original, then we have this result. So this is easier when F is convenient. Very easy when F is convenient. And how about if the map is not convenient? We do as follows. Firstly, we want to define the notion of mixed Newton number for the family of non-convenient polyhedra. So it is defined as follows. Let delta 1 to delta p be polyhedra in Rn. So this family of this polyhedra can be non-convenient. Then the mixed Newton number of this family is defined to be this formula. It is the limb sub the, the, the limb sub of the mixed Newton number of this family. So the idea is that I I add more monomial to each polyhedra here. So for each polyhedra I add the monomial on the coordinate axis. So alpha 1 to alpha n are the integral point on the j coordinate axis. So I add more monomial on the polyhedron such that the Newton polyhedron of this union are convenient. So if this convenient, if this union are convenient, then we have the notion of mixed Newton number, and then I take the limb sub when the exponent go to infinity. Then we define this number to be the mixed Newton number of delta 1 to delta p. It's not so obvious to see that this limb sub is not is finite, but it will it is it will be a corollary of the next formula that this limb sub always finite. Finite, yeah, it's always finite, and it will be constant when alpha when the monomial here are large enough. Then this sequence are constant. It is constant. Okay, our last theorem is the following. Assume that F to be any analytic mapping such that F is Kovansky non-degenerate and the zero set of F is a complete intersection with isolated singularity at origin. So in this case, we also have this formula for the minor number of F. It will be equal to the Newton number of the Newton polyhedral of Fi. But yeah, in the case of Kovansky non-degenerate and convenient, I do not need the notion to assume F to be complete intersection and isolated singularity because it's always true. If the map is Kovansky non-degenerate and convenient, then its zero set will be complete intersection and have isolated singularity as origin. But in this case, I need to assume this. This is okay. This is the last theorem, and now I will with the sketch of the proof. So the the most important theorem in our talk is this theorem. Is this theorem is the existence of the uniform stable rates of the family of some family connecting F and G. So. And I said that if in the case F and G are convenient, so this result is proved by Musu Oka using toric modification. And we also have another proof using the curve Sericin lemma. So that is the case F and G are convenient. So how about the case F and G are not convenient? So in the case of non-convenience, we do as follows. The idea is is not convenient, if the mapping F is not convenient, we will add to the component, to each component of the map F, some monomial. So say T to some exponent, new, and I will choose new large enough, large enough. Then we have this property. So this number new is choose large enough. Large means that its norm is bigger than this number, and this number is defined in this slide. I will go back to this line later, but let's see what we have in this lemma. So in this lemma, we consider this family. This family, the parameter is t. Then we say that when new is satisfied, when new satisfies this condition, then we have the family to be to have an uniform stable radius for the minimum vibration. And for mu also large enough, and for ht, the zero set of ft is a complete association. And if the function f, if the mapping f is not non-degenerate, then for generate t, the map ft is also non-degenerate. So this is the key lemma in order to prove the theorem 1. So I will tell you what is the number mu here. Mu here is defined from this property, So here we are considering the mapping f with isolated singularity as origin. Yeah. We don't assume anything else. So only isolated singularity as origin. 2 minutes. Yes. Then I denote M to be the maximum ideal in the ring of the analytic functions. And because F is has isolated singularity as origin, then we have this inclusion. So this is the Hilbert Nastanisat theorem. We have the inclusion, and therefore we can find a number mu such that the hi to the mu is contained in this idea. So this idea is some idea in this ring. Okay, so this is the key lemma to prove the theorem 1, and in order to prove the last theorem, so this is the last theorem. Yeah, so this is the last theorem, and the important points in this theorem is that f is not convenient. That in the case f is not convenient, we also use the idea, the same idea is that we add into f some monomial, some monomial on the monomial on the coordinate axis, such that the Newton polyhedral of the sum is convenient. Yeah. So and then we can find a family phi of t such that phi of t, the family phi of t have uniform stable radius, and then the minimum number of f will be equal to the minimum number of phi of t, and because phi of t is convenient, then we have convenient and Kowalski non-degenerate, and then the minimum number of phi t equal to the minimum number equal to the mixed Newton number defined before, and then we have the conclusion. Okay, maybe I stop here. Thank you for the attention, and once again, congratulations to Professor Osamu Saiki. Thank you very much.
Cảm ơn anh Thắng. Thank you very much for your very nice and interesting talk. So do you have some questions or comments? Yeah.
So this is a comment. The problem that the speaker is looking at here today about the constancy of the Milnor number when you deform above a Newton boundary or on the Newton boundary is a problem that has both a semi-local approach and an infinitesimal approach. And so in the semi-local approach, you do as the speaker did, which is to pick representatives and to work semi-locally to do things like bounding the Milnor radius. In the infinitesimal approach, you use ideals and modules that come from the vector fields associated with the problem. And it is often the case, in my experience, that the infinitesimal approach gives quicker and perhaps better results than the semi-local approach does. But both approaches are useful. For example, in the infinitesimal approach here, we can show that if it's convenient and Newton non-degenerate, then recommendations.
Sorry, I cannot hear you from now. I cannot hear you.
And then if you prefer, it's Whitney equisingular.
Sorry, Professor. I could not hear the last words. I cannot hear you. Do you have any question or remark?
No, the remark is just that there's two different approaches, and you have showed us how to do it in using the semi-local approach and semi-local methods. And I'm saying in the paper of mine that you cited, we use the infinitesimal approach using the integral closure of ideals and modules.
Yeah.
And there also we should mention Jim Damon's name, because he also had a different.
Oh, again, I cannot hear you. Right now, I cannot hear you, Professor. I cannot hear you, Professor.
You know, it's communication is very difficult here. We do the best we can. I just said that we should also using the Newton polygons to get those results.
Yeah. So sorry, I cannot hear all of the words, but because the mix, I don't know. But I did not know about the paper before. Maybe you are Professor Gaffney, right?
Yes, that's correct. I'm Terry Gaffney.
Yeah. It is my great pleasure to know you.
My pleasure to meet you as well. I guess I did have one question. Do you have an interpretation of some of the terms that appear in the formulas? The formula for the, in the convenient case, the formula for the mixed Newton number has many, many terms in it. Do we have an interpretation for those individual terms?
You mean the mixed Newton number in terms of terms?
Yes, that's correct.
Yeah. Yeah, that I don't know.
Yeah, there is. Okay.
I know that you are speaking, but I cannot hear you.
Yes. Perhaps we should continue by email. Thank you.
Yeah, thank you very much. Please write me email.
So, do you have any more questions or comments or remarks? So, thank you again, Thong, for your very interesting talk and for the discussion also. So, we thank the speaker again.
Thank you very much.
So, hello everyone. It is a great pleasure for me to introduce Nacho Breva-Ribes from Universitat de Valencia. He's a brilliant PhD student under supervision of Professor Raúl Osetziña, and he's working with a classical topic in singularity theory, which is the simplicity of certain map germs. And he's giving a talk entitled First Step on the Simplicity of Augmentation.
Thank you very much for the presentation. And thank you to the organizers for the opportunity of speaking here. I'm really honored. And so the title of my talk is First Steps on the Simplicity of Augmentations. That is because I will be speaking about augmentations and the relation to simplicity. And so the structure will first define what is an augmentation, what is known about the relation to simplicity at the moment. And we will continue characterizing A equivalence for augmentations. We will describe a method to build a versal unfolding for any augmentation, almost any augmentation. And then we will talk about some criteria for asimplicity. And so just so we are all on the same page, OM will be the ring of a local ring of functions. Theta M will be the space of smooth vector fields. And if we have a map germ F, theta of F will be the space of smooth vector fields along F. Again, F and G will be A equivalent if there exists germs of diffeomorphism in the source and target, such that this composition holds. And if we can take the psi as the identity, they are equivalent. And so associated to A equivalence, we can build these two mappings, which are just precomposition with the differential and postcomposition with F, and define these two algebraic spaces, which allow us to define the codimension, A codimension of the map term. And similarly, we can define the trinomial number as the dimension of this quotient right here, which is just the quotient over the Jacobian ideal plus the function. And so we can now introduce our subject of study, which are the operation of augmentation. It requires three ingredients. The first of which is a smooth map germ, F, which we will call the base map germ, and it is the germ that we want to augment. We must ask that it admits a one-parameter stable unfolding. So we will generally call it capital F, and we'll denote it like this. And the third and last ingredient would be a smooth function G. And so the operation of augmentation is just composing the function G in the parameter of the family of deformations of capital F. And then we say that a map germ is an augmentation if it lies in the A orbit of the augmentation of another map germ. Okay, just so we will write OPSU or OPSU to refer to one parameter stable unfoldings, just to shorten it. And so let's see an example of an augmentation. The most simple one would be taking the cusp right here. It admits a one parameter stable unfolding, which is just adding lambda times y in the last component. And then we can take any of these AK functions. And augmenting this map term would just be taking instead of lambda this function. And some of you may recognize it, this family of map germs as the escape family that appears in Mond's list of map germs from C2 to C3. And so one can play this kind of game of checking if your augmentation is, if your map germ is an augmentation or not. You can get a list of singularities and try to check which one of them are augmentations. And in this case, in Mond's list, you can check that the cross cap is the trivial augmentation via a regular function. The family SK, we already saw that are all augmentations. And also the BK and F4 map germs are also augmentations. It's quite easy to see that HK is not an augmentation for any K, and we will see why later. But CK is a little bit of a weird family, and for the moment, I would just want you to put a pin on that, and we'll come back to them in a minute. So how do we recognize that our map germ is an augmentation? Well, the first tool would be this inequality by Houston in 2004, which just it allows us to determine which possible map germs can be augmented to obtain our map germ. So it's just that the codimension of the augmentation must be greater than or equal to the product of the codimension of the base map germ times the trinomial number of the augmenting function. This is an equality if the augmenting function is Cauchy homogeneous or if capital F is a substantial unfolding. Being substantial is a condition on the liftable vector fields, which will not be important, and it's quite difficult to define. So just know that there is another condition that ensures the equality. But this allows us in the practice to kind of guess what can be the base map germ and the augmenting function, but we would like to see when something is an augmentation. And so we first, it's an easy exercise to check that every augmentation must admit a one-parameter stable unfolding. And Houston provided this theorem in 2004 in which he said that if a given map germ admits a one-parameter stable unfolding, then it will be an augmentation if and only if the analytic stratum of its one-parameter stable unfolding has dimension greater than or equal to 1, so positive dimension. The analytic stratum would be the tangent space to at the origin to the manifold along which F is trivial. But the problem with this is that we have found a counterexample to this theorem, and I'm going to explain it. So consider this map germ. You might recognize it from the list of months before. It admits this one-parameter stable unfolding, and it's an easy exercise to check that this unfolding has dimension 1 of its analytic stratum. And so, according to Houston, it should be an augmentation, but we have proven the following proposition, which is that every augmentation with up to, well, if a map germ is an augmentation with up to F bar, the order of tangency at 0 of the natural immersion with the manifold along which F bar is trivial must be equal to the Turner number of the augmenting function. And so what happens with this map germ? What happens is that the one-parameter stable unfolding is trivial along this manifold, which has order of tangency 2 with immersion. But doing some calculations with Houston's inequality, one can check that C3 can only come from an augmenting function that is of type Morse. So the augmenting function should have Turner number 1. So C3 cannot possibly be a augmentation. And what happens is that in Houston's proof, there is a lemma that is wrong, and the counterexample to the lemma is precisely C3. And so to fix it, we only need to take this lemma and kind of add it to the hypothesis. So what Houston does in the proof is that every map germ that admits a one-parameter stable unfolding with positive analytic stratum dimension, if we have this situation, we can always build a diagram like this, which would be a transverse fiber square in the lower row. This is the natural immersion. This is a commutative diagram that transforms our one-parameter stable unfolding into a product of a minimal stable map germ times the identity. And then finally, we can project over the first components to obtain another transverse fiber square. And so what we are interested in is this composition right here on the right column. So to fix Houston's theorem, we only need to add one extra condition. If a map germ admits a one-parameter stable unfolding, it will be an augmentation if and only if the analytic stratum of the OPSU has positive dimension, and the analytic stratum of the composition that I was talking about in the last slide has dimension greater than or equal to P minus D, where D is the analytic stratum. Okay, so now if you come with a map germ and you want to know if it's an augmentation, we know how to check that. So now we can begin to talk about simplicity. Roughly speaking, simplicity, asimplicity, means that every possible singularity that appears when forming a map germ lies on a finite number of left-right equivalence classes. And so we're interested in checking when the resulting augmentation is simple. And so one would think that if the ingredients to build the augmentation are simple, the resulting augmentation should also be simple, but this is not that easy. Consider this map germ. It admits a one-parameter stable unfolding like this. This is very simple. It's known by everyone, and this is one of the simplest functions you can think about. But the resulting augmentation is this map term that is not on Mond's list of simple map terms, and is therefore not simple with respect to A equivalence. And so the only result that was related to simplicity before these results that I'm going to talk about is this one, by Jose Duras and Wikatik. If you have a smooth map term that admits a one-parameter stable unfolding, given two smooth functions, the augmentations will be equivalent. If the augmentations are equivalent, then the augmenting functions must be contact equivalent. This means that if the functions are not contact simple, then the augmentation will also not be simple. But we would like to kind of get a stronger result, maybe, because usually when one speaks about simplicity of functions, we speak about right equivalence. So we will come to that in a moment. So definitely our goal is what conditions can we impose on f and g to ensure that the augmentation is simple. And so we're going to talk about how to check that two augmentations lie on the same A equivalence orbit. Our first result will be that if f is a smooth map term that admits a one-parameter stable unfolding, given two smooth functions, if the functions are right equivalent, then the augmentations will be A equivalent. This is the proof is really easy. It's an exercise of the definitions, but it's really interesting because it allows us to prove this corollary. In the case that G is R equivalent to a quasi-homogeneous function, or again, if capital F is substantial, then we know how to compute the codimension of the augmentation. It's exactly the product of the codimension of the map term times the Turnerian number of the augmenting function. So this is a very useful result. And we can get a kind of a partial converse to the previous proposition, adding an extra hypothesis. The extra hypotheses are that both functions have isolated singularity and that they are both are equivalent to quasi-homogeneous functions. In this case, the two augmentations will be A equivalent if and only if both augmenting functions are equivalent in the complex case. So this is similar to what we had in previous the first proposition, which had K equivalence. We can omit the K equivalence, adding this extra hypothesis. And another way that we can check that two augmentations lie on the same A orbit is comparing their one-parameter stable unfoldings. So in this case, we have to restrict ourselves a little more. We work over the complex numbers, and if we assume that the base map term has A equal dimension 1, and that G has, again, a selected singularity and is R equivalent to quasi-homogeneous function, then the augmentation of F via the augmented function G does not depend on the chosen one-parameter stable unfolding. This result relies strongly on the fact that in codimension 1, every one-parameter stable unfolding is also a universal unfolding. And this allows us to, well, this behaves very well with augmentations, and it allows us to prove the result. But it's not easily translatable to other codimensions. And so we know how to check now that two augmentations lie on the same A equivalence orbit. The only thing that we have left to begin to talk about simplicity is to build a versal unfolding. And so, again, the setting will be on the complex numbers. We will have F a smooth map term, capital F a one-parameter unfolding, G a smooth function. What we want is constructing a versal unfolding for the augmentation. How do we do this? Well, first, take the codimension of F to be the number K, and take the Turnerian number of G to be the number R. What this means is that we can find some vector fields along F, gamma sub I, such that their class over the normal AE space span the whole space. And we can find some tau sub j monomials such that this quotient is spanned by these monomials. And so how do we build a Bersolon folding? We take the vector fields along F, and we generate the normal AE space of F, and we multiply them by the monomials that span the quotient associated to the Turner number of G, which we have right here. And we multiply them, each one of them, by a parameter, and then we get this formula for a versal unfolding. And to show you that it is a powerful result, well, let's build an example. So take this plane curve, this family of plane curves. They will admit a one-parameter stable unfolding, capital F, and take any of these smooth functions. The resulting augmentation has this structure, and trying to compute the versal unfolding, it's not really difficult, but it would take some time, and it can be a pain. And with a result, you need to compute the normal space to the map germ, the algebra associated to the Turner number of G, and we can easily check that this is the versal unfolding of this augmentation of this whole family. In this family, we have SK functions on month list, F4, F4, and DK functions. We have all the simple functions and more that are non-simple. So we can build easily some versal unfolding. Okay, and now I can begin to talk about simplicity. So we will be still working over the complex numbers. So let F be a smooth map germ with one parameter stable folding capital F. This first proposition give us a condition on which how to say when the augmenting function will not be simple. If the augmenting function is not R simple, then the augmentation won't be simple either. So notice that when we were talking about before about the equivalence between augmentations and functions, we had to add the hypothesis that the augmenting function were with isolated singularity and quasi-homogeneous. In this case, we can drop this assumption. So if G is not R simple, the augmentation also won't be simple. And to speak about proper simplicity and not the lack of it, we first must realize that every deformation that appears in the versal unfolding of an augmentation, in these two cases, is also an augmentation. This is a really easy proposition. You just need to go to the structure that we gave for the versal unfolding, and you see that if F has codimension 1, or if the Turner number of the augmenting function is 1, then this is the case. Everything that appears around F has the structure of an augmentation. And these augmentations are augmentations that result from a deformation of F via a deformation of the augmenting function. So we know everything that appears around the augmentation. And this allows us to prove in these two cases, first, that if we are in the nice dimensions and F has codimension 1, then the augmentation will be simple if and only if the augmenting function is simple. This restriction on the nice dimensions is because out of here, you can find codimension 1 map germs that are not simple, and things get a little bit tricky. Well, it's a characterization in this case. And the second characterization would be that if the augmenting function is Morse, then the augmenting function will be simple if and only if the base map germ is simple. So this proof is actually, I think, quite nice because it's by induction, which is something I didn't expect that would work, but it does. Okay, so what happens outside of these cases? Outside of these cases, what happens is that in the versal unfolding, some deformations that appear are not augmentations. And this is a problem because then we cannot say anything with our results about these deformations. In fact, the first example that I showed you before, the augmentation of a simple map germ that resulted in a non-simple map germ, The problem with that function is that the stratum that is not simple is precisely on the part of the versal unfolding that has no augmentation. So it seems that, like, out of these cases, something can happen that breaks the simplicity. And so, just to finish, I wanted to show a little exercise that we did, kind of a conjecture, and it comes from this observation. In both of these classifications, the K2 to K2 from Rieger and K3 to K3 from Mararantari, all the present augmentations in this list are either augmentations of a codimension 1 map term or augmentations via Morse functions. And so what we have done is to build a conjecture on which map terms are simple augmentations in K4 to K4. So this would be the list of all possible simple augmentations in principle. Okay, so this would be it. This talk was based on a paper we have sent for publication with Raul that is available on archive if you want to read it. These are some references. And so this would be it. Thank you very much.
Okay, thank you very much, Nacho, for this nice talk. Is there any comments or questions from the audience?
Thank you, Nacho, for the talk, very nice talk. So it's not very clear for me why you need over the complex result like F is simple if and only if the augmentation is simple. Why it's not? Why it does not hold in the real case?
In
for
this
instance, this, yeah.
Well, in this case, I mean, the result that for which we build the versal unfolding, it's only for the complex case, and so this proof relies strongly on the form of the versal unfolding. I guess that in the real case, the versal unfolding is the same, but I have not proved it yet. So, as this, I have only written this for the complex case because the versal unfolding is only proof for the complex case. And the proof relies on the
your result about the versal unfolding.
Yeah, this result. This one. It's in the complex case, yeah.
And why is this result for the complex case?
I think it's also for the real case, but the proof relies on the fact that I can expand as polynomials the components of the different vector fields along the augmentations, and then compare coefficients of these polynomials. And so there is some steps there that I think that can only be done in the complex case. Maybe there is another way to prove it, but I didn't find it. So yeah.
At least in the real analytic case, maybe.
In the real analytic case, it translates directly. Yeah, totally.
Okay.
Yeah, but if it's only smooth, then I
okay.
Is there any other question or comment from the audience? Well, if not, let's thank the speaker again, please. Okay. Stefana, can you hear me?
Yes.
Hi.
Hello. Can you
Well,
hear me?
it is a great pleasure for me to introduce Miruna Stefana Sorea. She's a postdoctoral researcher at the Scientific Research Institute SISA at Trieste, Italy. And her main research interest is real algebraic geometry and applications, geometry and topology of real singularities, algebraic statistics, and dynamical systems. And she's gonna give a talk entitled Poincaré-Rive graphs of real algebraic domains.
Hello. Thank you very much for the introduction. Can you hear me well? Okay. So I am honored to present today my research in this nice event. Thank you for the invitation. And I will start by wishing, I'm honored to wish happy birthday to Professor Saeki, whom I met in 2018. I had the honor to meet him at the 6th Franco-Japanese-Vietnamese Symposium on Singularities in Vietnam. And I'm happy to be able to wish him today happy birthday. So this is a work about Poincaré-Rive graphs of real algebraic domains. So I will give a short motivation and the starting point. That was so the beginning of this work was in my PhD thesis, and these results were published in these three papers that I wrote here. And now, so after a brief discussion about the previous results, I will talk about a joint work with Arnaud Baudin and Patrick Popescu-Pampu, who were my PhD advisors in Lille, and where we generalized the results to real algebraic domains. I will explain what I mean with this. So, as I promised, the starting point is this effective construction in the case of strict local minima. So let me tell you what the objects that I consider are. So that this was in the beginning. So in the previous work, I was considering functions that were bivariate with real coefficients, polynomial, vanishing at the origin, and having a strict local minimum at the origin. And I was looking at the real Milnor fibers at the origin. So small enough level curves, f equals epsilon, for sufficiently small positive epsilon, in a small enough neighborhood of the origin. So these real Milnor fibers are smooth Jordan curves. And when this strict local minimum is a Morse strict local minimum, the small enough levels become boundaries of convex topological disks, and we call them convex curves by abuse of language. And the question is whether this happens also when the strict local minimum is non-Morse. That was the starting point of my of this research, namely a question by Emmanuel Giroux, who asked Patrick Popescu-Pampu in 2004 whether the small enough level curves of f near strict local minima are always boundaries of convex topological disks. The answer to this question is negative, and this is due to a counterexample that was found by Michel Coste, who gave this polynomial that is bivariate, has a non-Morse strict local minimum at the origin, and here are some of its level curves. So its level curves will never become convex when they approach the origin. So the main research problem that I want to present that I'm interested in and I'm presenting today is so the main goal of this whole research is to understand this non-convexity phenomena in full generality. That is the main goal. As previous results are the fact that I constructed and characterized non-Morse strict local minima whose nearby levels are far from being convex for a large family of such polynomials. So for instance, here, just to make an idea, so that you can make an idea of what I mean, already. So this was cost counterexample in the left figure. And now in the middle, we see already some more complicated shape. And on the right hand side, we see already other types of shapes where some symmetry arises and where you can realize that it is, you can say it's more non-convex than the previous one, let's say, like this. So somehow we are led naturally towards this question of measuring the non-convexity in some sense. So the question now is, what combinatorial object can encode the shape and measure the non-convexity of a smooth, compact, connected component of an algebraic curve in the real plane? And I will show you what object I considered and introduced. Namely, it will be a tree. It's a graph, but in that case of strict local minima, it turned out that it is a tree. And I called it the Poincaré-Reb tree. And now, once I had this tool, the graph, I rephrased the problem in terms of trees. So the main problem becomes to characterize all possible topological types of Poincaré-Reb trees. And the second subproblem, the subproblem that I mentioned above, is the following. So given such a tree, an abstract tree, can we construct a bivariate Morse, bivariate polynomial, that has a strict local minimum at the origin that realizes the given tree? And in the previous results, I gave a positive answer to this question, to this construction problem, and I gave an effective construction. So for a large class of such trees, so namely for the separable transversal trees that are also generic. There are some technical, here are just some technical notions. And for separable generic transversal trees, we can construct the equation of a real bivariate polynomial with an isolated minimum at the origin that realizes the given tree as its Poincaré-Reb tree. So this was the effective construction in the case of strict local minima. It involved tools such as the polar curve, the discriminant curve, and the combinatorics of contact trees between univariate polynomials. I don't get into details now. In any case, different tools than in this talk. And then we were led naturally to this question: what can we say about the non-convexity of a general domain? We wanted to generalize this and construct more general shapes. And this is the joint work with Arnaud Baudin and Patrick Popescu-Pampu from there at Université de Lille. And you can find our work in the archive. This month we uploaded it at this link here in the bottom. Good. So let me briefly give an idea of what the main result is. So let's see the question. So given a compact, connected, generic, transversal graph G in a vertical plane, does there exist a compact algebraic domain that realizes this graph as its Poincaré-Reb graph? So for this question, our answer is yes. I didn't tell you exactly what kind of graphs I mean. I will explain soon. So we give a positive answer of a realization. This is a realization result. It's not effective realization, but we prove that it can be realized. Now you might wonder, why do we care about these problems? So I just want to give a brief motivation. First of all, it can have very nice applications at some point in non-convex optimization. So it might be, these might be important, useful tools for these questions in non-convex optimization. Moreover, as we will see the Poincaré graph that I will define in briefly, in short time, is a complete invariant for the vertical equivalence. I will tell you how we consider this equivalence. And this shows that it can be a useful tool in our study. Moreover, it turns out that it is also useful as a tool to compute the Euler characteristic of the domain we are considering, and to compute Bethe numbers and study the topology of the domain. Moreover, not only you can study the topology of the given domain, but it is useful for studying the combinatorics of the complement of the domain. You can deduce nice properties about the complement of a domain using the Poincaré graph. And I will explain to you how. Okay, so now this was the motivation and the starting part. I need to explain, to give the definition now of Poincaré graphs of real algebraic domains. This is the second part of the talk. So in this case, we want to generalize. Before we were considering real Miller fibers. So we were talking about strict local minima and nearby level curves and the disks, the topological disks bounded by these curves. But now for us, the objects of study are algebraic domains. We denote them by calligraphic D in what follows. And they are closed topological subsurfaces of a real affine plane. And their boundary consists of disjoint, smooth, connected components of real algebraic plane curves. So already you can see here some examples. We can see an algebraic domain in the left hand side, where its boundary is given by 3 ovals. We call them like this, ovals. Then in the middle we have a non-compact algebraic domain, D, whereas in the third case we even consider non-compact and not connected algebraic domains that we will tackle along this talk. A concrete example of an algebraic domain. It will be this ring surface here in gray. And let me tell you how to define it. So for instance, you consider this curve, real algebraic plane curve, that is given as the zero locus of this polynomial here, C1 bar. This is the red curve here. It has 2 connected components, an oval and a component homeomorphic to a line. And we also consider the second curve, that is the blue one. Okay, and this one also has 2 connected components as the red one. Okay, but now if we consider the ring surface bounded by the 2 ovals, the red oval here and the blue oval, we obtain by definition an algebraic domain. So with this, I want to underline the fact that this is more subtle, in the sense that algebraic domains are a bit more general than semi-algebraic sets. It can happen that we ignore this line, the red line, and we only consider the gray surface here, without any problem. So this is an example of an algebraic domain. And now these are the objects we are looking at. And what is our goal in the next, in what follows? So again, we want to measure the non-convexity, but of algebraic domains. This task is quite complicated, and that's why we decided to measure this non-convexity in a certain direction of projection. So we will usually consider the vertical projection and work with it. and we will measure the non-convexity in the vertical projection direction. Again, we ask ourselves what combinatorial object could encode this non-convexity, could measure how far from being convex an algebraic domain is. And the idea is similar. It's the same idea as I had in my previous work, where we will collapse inside the domain the maximal vertical segments that are contained in the domain. Maybe a picture is better. In this picture, we can see how we collapse, for instance, for each vertical segment in the pink area, we get a point, and you get this segment. So let me, maybe I have a better, a clearer picture. And now is the moment to define the Poincaré-Reb graph. This is the object that will measure the non-convexity in our work. So in this case, I drew just a disk because that was the beginning of this study. Now we can have, as you saw, more complicated objects, but the same idea holds in the sense that we collapse these maximal vertical segments inside the domain. So we have this vertical projection that you can see in this slide, and we have a point on the horizontal axis, x0. Now, if we look at the pre-image of this point inside the domain, it, for instance, in this case, it is a union of two vertical segments, the green and the pink segment. Okay, now what we do, we pass to the quotient, and essentially we contract each such segment into a point. So the green segment becomes this green point on the graph. The pink vertical segment here will become this pink point on this edge of the graph. And we proceed like this with all the points. In the end, what we do is we contract the whole domain into a graph. Okay, so here it is. The vertices of this graph, by definition, are the points where, so the images of the points of vertical tangency on the curve, on the boundary of the domain. So this is the object that we are working with, and notice that. So yeah, in my PhD thesis, I named it Poincaré-Reb graph because it is inspired from the classical construction that was used in Morse theory as a tool by Poincaré. He introduced it for 3 manifolds, and then it was rediscovered by Georges Reb, for arbitrary dimension, and they were using it, as I said, as a tool in Morse theory. Now, in this setting, so what I want to say here is that once you get to contract these vertical segments, you will obtain a canonical definition of the Poincaré-Reb graph. However, this definition, so this new graph, so this graph, will no longer live in the same plane, a fine plane, as the initial domain. So we have here, once you contract these segments, a new plane homeomorphic to the initial R2, but it's not, you cannot canonically obtain the starting plane. Okay, so this motivates us to, so for some generic trees, I will soon say what that means, but for these generic trees, this motivates us to consider Poincaré-Reb graphs in the source. What I mean by this is that it is possible to lift the graph to the starting plane by considering here these edges inside the domain. Essentially, you will consider the section of an isotopy that fixes the vertical lines. In any case, the advantage of this new definition is that this new graph lives in the same vertical plane as the domain. And in some cases, we will need this. Also, I would like to stress the fact that notice that it is this construction is a graph, so it might have cycles, okay, and yes, you can see here an example of such of the Poincaré graph as I defined it initially, and of a Poincaré graph at the source in the middle. So in the bottom we have the canonical definition, and in the middle we have one of the Poincaré graphs in the source. So I said that this is inspired from the classical construction of Poincaré and Reb, but in our setting we have some more properties. So essentially the most important ones are that these graphs are transverse to the foliation induced by this function x, so transverse to the vertical foliation. The open edges are transverse to the foliation. And moreover, one should keep in mind that the pre-order induced by x on the points of vertical tangency descends to the quotient on the vertices of the graph, so that the vertices will be endowed with a total pre-order relation. Why is it just a pre-order where we can have multiple vertices on the same vertical line? So in general, and we will want to avoid this by considering generic graphs where we avoid this situation, where we have multiple vertices. Just a couple of slides. I want to mention briefly what was happening in the case of strict local minima. So there, remember, I was just for these two slides, I want to mention that we were considering small enough level curves near a strict local minimum in the beginning. Well, in that case, if for each such level curve you associate a tree, sorry, in that case, it turns out that it is a tree, it's this graph. So you associate to each level such an object, a tree, and starting with a certain level, epsilon, I proved that actually these trees are become equivalent. They don't change anymore. The shape stabilizes. That's why I say that the asymptotic Poincaré tree stabilizes. Moreover, in that case, it is a rooted tree, since I mean the image of the root, so the image of the origin is the root of the tree. And what is even more interesting is that asymptotically, we cannot have spiraling phenomena. So we have some strict monotonous preorder on the geodesics of the tree, starting from the root towards the leaves. So we cannot have these configurations locally when we consider strict local minimum. Moreover, also in that case, I was considering some generic projection, and if the projection is generic in the sense that there are no two vertices on the same line, then the tree becomes complete binary. So each vertex has exactly two children, and the vertices become endowed with a total order relation. So we no longer have a pre-order, but an order relation. Okay. Now it's time to pass a bit to the most general setting that I will present in this talk. So you see that these graphs are. It gives you already maybe the idea that you can define such objects also in more generality, and in what we want to do now is I will show you that we can study the Poincaré graphs without any differentiability hypothesis and just for domains where the minimum of conditions are imposed, such that we still obtain an embedded graph in the plane and with finitely many vertices. And since I explained to you that this graph will live in a new plane homeomorphic to the initial affine plane, we want to define now what a vertical plane is. So we are motivated by this fact that new planes appear all the time and that we can work in a more general setting. For us, a vertical plane is a pair P pi, where P is a topological space homeomorphic to R2, as we would obtain when we collapse these segments. It is endowed with an orientation, and the projection pi is a locally trivial topological fibration for us. We call it a projection. The canonical projection for us is this X projection, the vertical one, that sends xy to x. And of course, R2 is the canonical affine vertical plane. As I said, the motivation is that after this collapsing procedure, we end up with the new vertical plane. Now, in order to give the general setting where we study Poincare-Reb graphs, I need to give one more definition here, namely the topological critical set of a curve. So now, if we consider C to be, so this calligraphic C here, just we consider a closed submanifold of dimension 1 of the plane, then the a point P of C is a topological critical point if in its neighborhood the restriction of this map pi to the curve is not a local homeomorphism onto its image. So you can see P1 and P2 here. They are topological critical points of the curve C. So when you project with pi, say the vertical projection on the horizontal axis, you can see that the projection restricted to C is not a homeomorphism onto its image. And as a counterexample, the point Q is not a topological critical point for us. I mean, according to the definition. We care about this because topological critical points will be vertices of the Poincare-Reb graph. That means that in this case, we ignore such points of tangency. And now, these are the domains that I want to present. So, domains of finite type. So, if we consider a vertical plane, P pi, and we take a closed subset, homeomorphic to a surface with boundary, non-empty boundary. What do we call a domain of finite type? That's a generalization of what we considered before. So we say that D is a domain of finite type in this vertical plane if the following two conditions hold. So we want that the restriction of pi to the domain is to be a proper map, and moreover, we want that it has that the topological critical set to be finite. So we want only finitely many topological critical points of the domain. And we call the domain generic if there are no two topological critical points on the same vertical line. So here in this picture, we have an example of a domain of finite type, here D. You see that it respects our definition. The two conditions are fulfilled. Whereas now, I also show you in this slide two domains that are not of finite type, because the restriction of the vertical projection to the domain is not proper in both scenarios. Great. So now I was telling you in the beginning that there is that the Poincare-Reb graph is complete invariant for the vertical equivalence. Now, why do I talk about the vertical equivalence? Now, the vertical equivalence that I'm going to define, the purpose of it is to capture the combinatorial structure of subsets in affine planes. What I want to say is that two vertical equivalent subsets have the same combinatorics for us, the same combinatorial type. And let me tell you now what that means. So if we have two vertical planes, P and P prime, and we have X prime, two subsets in these planes. So here you can always imagine R2 instead of P and P prime, so that you simplify and consider pi and pi prime to be the projection X. Then we say that X and X prime are vertically equivalent if there exist orientation preserving homeomorphisms such that they make this diagram commutative and such that phi sends X to X prime. So we have phi, we have psi, and essentially we want to, the key idea is that we want to preserve the horizontal order with this vertical equivalence. So in other words, if we have 2 points, Pi and Pj in the first set, such that their abscissas X are in a certain order, then their images via phi will preserve this order of the abscissas. Okay? And for us, it is important from the point of view of topological critical points. We will want to preserve the order of the topological critical points. This is what matters in our talk, in this talk. So finally, as I already mentioned, I can state now the proposition that tells us that for this vertical equivalence relation, the Poincare-Reb graph is a complete invariant. So we have that two domains of finite type are vertically equivalent if and only if their associated Poincare-Reb graphs are vertically equivalent. And with this proposition, we can now deduce, if we are given, for instance, two domains, such as these ones that are homeomorphic to disks, that they are not vertically equivalent. And how to do this? Well, just construct their Poincare-Reb graphs. If you want, you can construct a Poincare-Reb graph in the source, so inside the disk. I just drew them here outside. And you can notice that the two graphs are not vertically equivalent, because you notice here that here we have this 3, 6, whereas the other one appears in a different way in the middle here, 3, 6. And in order to pass from one to the other, we would obtain two vertices on the same vertical line. And that's not possible. So that means that these domains are not vertically equivalent. Well, if we use now this complete invariant proposition. Great. Now, you might wonder whether this is, maybe some simpler objects that can be complete invariants exist, and maybe why we don't take those into account. And we found some other invariant, for instance, but it was not, in the end, it turned out that it's not a complete one. So let's see what this is about. So we still work with these two disks from before, where you notice that the topological critical points, which are here the points of vertical tangency, in this case, are numbered in red. So if you follow the contour, if you follow the boundary of the surface, we have 1, 2, 3, 4, 5, 6, the circular order. And we would like to get a permutation from this object. And what we do now is we use some method that was is described, for instance, in Knuth's book, and also mentioned by Etienne Gis in some other context in his recent book, A Singular Mathematical Promenade, where the idea is to consider a set of objects and to endow this set of objects with two total orders. So the first total order in this case, I mean, the set for us, of course, is the, as I said, the red points here on one curve. And the first order is the circular one, as I showed you, whereas we also have a second total order endowing these points, and this is the one induced by the vertical foliation. Just consider the standard order here in green on the real axis. So we have 1, 2, 3, 4, 5, 6. Now, in order to get a permutation, you compare these two total orders. So you see that the vertex labeled 1 is in the first position. So you say 1 goes into 1. Then on the second position, we have the vertex labeled 5. So 2 goes into 5. 3 goes into 3 here. 4 goes into 6. 5 goes into 2. And 6 goes into 4. So we have our permutation. If you do the same procedure on the right-hand side, you will obtain the same permutation. Okay, so what does this tell us? Well, it tells us that although these two objects have the same permutation, but we knew that they are not vertically equivalent because they had different Poincaré-Reb trees. This means that this object, this combinatorial object, is not a complete invariant. So it's not so straightforward to find a complete invariant of domains of finite type. It will here I mentioned that for the compact case it was a complete invariant, but we will also we also proved that also in the non-compact setting it happens the same. Good. And another advantage of this of the study. So why is it useful, this Poincaré-Reb graph? Well, you can also notice the invariance of the Euler characteristic. That means that if you're given a domain of finite type and you consider its Poincaré-Reb graph, then they have the same connected components, and then they have the same Euler characteristic. And the idea of the proof is to use integration with respect to the Euler characteristic. I won't go into the detail with this proof, but that's the key strategy. Moreover, so using this invariance of the Euler characteristic, what we obtain as a corollary is what I proved previously, that when the domain is a disk, a topological disk, then the Poincaré-Reb graph is a tree. There are no cycles. This comes as a corollary of the previous proposition. Now. Okay, so now I explained what the objects that we are working with are, and I defined the Poincaré-Reb graphs of real algebraic domains. And we are ready now to see the algebraic realization part in the case of compact, connected, generic transversal graphs. The idea is that so I will explain what this generic transversal means. Compact and connected is clear. So let's think of it as the compact setting now. Later on, I will also give the generalization for the non-compact situation. So the main theorem that I want to present now is the following. Any compact connected generic transversal graph can be realized as a Poincaré graph of an algebraic domain. So with just the help of the pictures, given such a graph, we can construct, we don't give a precise and effective construction, but we show that it can be realized by an algebraic domain. Okay. In the case of compact connected generic transversal graph. What I mean by generic? So generic graphs are, for us here, graphs whose vertices have only valency 1 or 3 and whose and who have no two distinct vertices on the same vertical line. So for us, this means generic. And what I mean by transversal graph is, as I also stated previously, that it's, so roughly speaking, that its open edges are transverse to the vertical foliation induced by X on the plane. This is the realization theorem. Just an example of a non-generic case, because so what is obvious that, I mean, it's not difficult to prove that the Poincaré graph is generic if and only if the domain has no two topological critical points on the same vertical line. So here I just give you an example of a non-generic case, which will give rise to a non-generic Poincaré graph. So maybe now I will mention some words about the strategy of the proof. So there are 3 steps in the proof, and as follows. First step is just to recall, we have a graph, generic, transversal, compact, connected, and we want to realize it via real algebraic domain. Now, the first step, it will be to realize this graph by a domain of finite type that is given by a smooth function. First, we don't go directly to algebraic, but we realize it by a smooth function. Then the next step, we will use a classical result, that is the Weierstrass type theorem, okay, Stone-Weierstrass theorem, that tells us that we can approximate any smooth function by a polynomial function. However, this will not suffice, because for us the points of vertical tangency, so the topological critical points, are important, and when we approximate the smooth function with this polynomial, so we take the level of this, say, this polynomial p, and we take p equals 0, and it might happen that p equals 0 has many more or different vertical tangencies. So we are not done with this because of this situation. We don't have already the proof, but the third step tells us, I mean, what we do is we adapt this theorem from step number 2 so that we can control the vertical tangents. In this way, we realize the graph as the Poincaré graph of a generic finite type domain that is algebraic. These are the main 3 steps of our proof. So maybe I don't go into all the details here. The idea, so the first step, first of all, we will construct. So we wanted a smooth function that realizes it. Well, first we will construct a curve, okay, that has the desired shape, and then we will construct the function, the smooth function f, that makes this curve gives such that the level of this function f is the curve we constructed. So the curve C that we want to construct, so given a graph, okay, we want to construct a curve C that is compact, that is included in the neighborhood of the graph. Okay, here we consider this graph at the source. We work in the plane. Now we want this curve to have only one vertical tangent associated to each vertex of the graph. And then we also want to preserve the order of the vertices of these tangencies. So again, okay, here the last condition, if you take the neighborhood small enough, epsilon small enough, you will not have problems. This is no problem. The main point is that we construct this curve C, by interpolating some local constructions that we make in the neighborhood of the vertices. Okay. And here is the precise statement. Maybe I skip this. And moreover, yes, these are some technical details. Maybe it's better to... Maybe I'll come at the end back to this. Now, for the second step of the proof, we have, as I said, a theorem, a classical result by Stone-Weierstrass that says that we can, there are some hypotheses, but the idea is that we can approximate, if we have a function from R2 to R that is continuous, okay, then for each epsilon, we can get close with a polynomial, close by f, as close as we want. And actually, to prove this, as I said, this is the previous proposition, is a corollary of Stone-Weierstrass theorem. This is a well-known result, Stone-Weierstrass theorem, and maybe I don't go into this detail. But so once we have that, we can go to the third step, as I mentioned, and to adapt this polynomial actually that we can find so that it has the vertical tangencies exactly where we want. So we have this neighborhood of, so we have the previous construction of the smooth, given by the smooth function in red. We have this neighborhood in red of the function, of the level f equals 0. And now the key point is to get this polynomial p such that p equals 0 behaves the way we want. So it's a bit technical, but maybe I will just say roughly what we prove. So the idea is that if we have this function f and which has only simple vertical tangents, is included in the interior of a compact subset of the plane, then for each delta, remember that here we had this neighborhood, delta neighborhood, there exists a polynomial p such that the intersection of the zeroth level of p with this compact subset k is included in the neighborhood. Moreover, we have a vertical tangent for each vertical tangent of f equals 0, there is exactly one vertical tangent of p equals 0 in this, okay, in the neighborhood. And then moreover, there are no other vertical tangencies for p equals 0 in this compact subset. Maybe, I don't know how much time. The idea would be that we replace, and so this third step has also 3 small steps. The idea is first to replace the function f by a function g with compact support. Okay, this is quite a classical step. Then, how do we define this p, this polynomial that we care about, such that it has this controlled vertical tangencies? Well, we apply the corollary coming from the Stone-Weierstrass theorem to this function, where we take these partial derivatives of the new g function from before. And we obtain a polynomial p0 then we can define P to be these integrals of multiple integrals of P0. I don't go into the technical details more than this, but the idea is that the new polynomial P with real coefficients has indeed the properties I announced. So in the neighborhood of a vertical tangency of f equals 0, we have a vertical tangency, a unique vertical tangency for P equals 0, whereas in the left-hand side of the picture here, if f equals 0 has no vertical tangency and no other, let's consider just vertical tangency, then neither P equals 0 has one. So there's the shape we want. Finally, so this was the study in the compact connected setting. Now we were also able to give a realization theorem in the non-compact case if the domain is simply connected. But let me introduce now some generalized domain that actually does not impose anymore that the projection restricted to the domain is proper. But in this case, we want that the projection restricted to the boundary. So we only want that the projection restricted to the boundary of the domain to be proper. The rest stays as it was. So this is what we call a domain of weakly finite type. And here we have some examples of domains of weakly finite type. These three pictures. You can see that this is the non-compact case. And again, the genericity definition is again that we don't want to have two topological critical points on the same vertical. In this setting, when the boundary of the domain is homeomorphic to a line, so we have just we have one connected non-compact curve as the boundary of the domain, we distinguish three cases of domains of weakly finite type. So I pictured them here, and what I want to mention is that in this case, the Poincare graphs need to be enriched. So we cannot use only the previous ones, because in this setting we have unbounded edges, and we have in this second picture, for instance, unbounded segments that we want to consider inside the domain. And we would like to keep in mind which of the sides of the, okay, maybe they're not good to call them segments or semi-lines. Okay, so which of the, where is it, this unbounded line going? Okay, so that's why we have two types of enrichments. So first of all, we have arrows of the edges, so some vertices become arrows. So we have arrowhead edges that show you that this is that is a component that goes to infinity. Moreover, we also endow these edges with what we call feathers, in the sense that we add feathers in the side of the edge that is unbounded, as you can see in this picture. And there are these three cases that we will consider in the following. Okay, so now the realization, the algebraic realization theorem that we have in the case where we consider simply connected domains which are non-compact is the following. So if the idea is that if we use the previous construction for the compact part, and we can add branches towards infinity, then we can realize these three cases from before. with some technical condition here that we want the compact part of the graph, roughly speaking, to be realized with the previous construction, but by a connected real algebraic curve. So not just by a component of a real algebraic curve. Okay. The main idea would be to consider such an ellipse. I will show you on a very simple example, the idea that you consider if you have an ellipse, you would like to add branches towards infinity to this ellipse. Well, what we do, we take a line, say g equals 0, and then consider f equals 0, f equals 0, g equals 0. Take the product f times g equals 0, then this gives you the union of these two curves. Moreover, when you take a neighboring curve, f times g equals epsilon, say, or minus epsilon, depends where you want, in this third picture here, you will get branches towards infinity. So this is just roughly the idea. In particular, for each of the three cases, there's a special curve you need to consider. Maybe I don't insist too much on it, but sometimes you take a parabola, maybe another time you will consider a horizontal line for constructing this second case, whereas for the third setting, here you will notice that we have a complementary setting with the first one. So you get it for free. This is the strategy of proof for the non-compact and simply connected case. Already I mentioned something about complements. So now is the right moment. I'll just briefly mention now that when you consider general domains, okay, so such as this one, where we have non-compact and I'm done.
Can you hear me?
Yes,
I'm sorry. You have 5 minutes left.
Thank you. Yes, I'm almost ready. So when you consider this set, the most general case where it's not connected, might be non-compact. Okay, the graph becomes can have several components, and what we prove is that actually the interior. So what we call we have a domain. You take the Poincaré graph at the source as this blue one. If you consider the complement of this domain and you take the Poincaré graph of this one, then it turns out that the interior, so the first graph determines the graph of the complement. So this is a nice way to understand the complement of a domain. And just the last thing I want to say is that this graph, the Poincaré graph, is a nice tool to help you. And so we have a technical formula that actually tells you, in function of the graph, you can recover the number of lines, the number of ovals in the boundary of a general domain. Okay. So to sum up, we started with some problem in near a strict local minimum to understand this non-convexity. I introduced this Poincaré tree that was that I constructed with some effective realization of polynomials for a large class. But then we wanted to generalize this, and in a work with Arnaud Baudin and Patrick Popescu-Pampu, we considered algebraic domains where a similar idea of construction, we used a similar idea of collapsing the vertical segments, and where we could give a realization theorem both in the compact case and in the non-compact setting where we consider simply connected domains. With this, I would like to thank you for your attention and to wish again a happy birthday to Professor Saeki. Thank you very much.
So, is there any question or a comment for the speaker?
Thank you for the talk. In your construction in the step 2, where you use the Stone-Weierstrass theorem, I think there's a stronger version of the Stone-Weierstrass theorem, which is perhaps less well known, which combines interpolation and approximation. So it allows you to fix the values of the functions and values of derivatives of the function at fixed points. And I think if you use that stronger version of Stone-Weierstrass theorem, you don't really need to use the step 3 where you justify these vertical tangencies, because you could just fix the values and the derivatives on the points where your original function has vertical tangents. And then that version of Stone-Weierstrass would imply that there's a polynomial which not only has vertical tangencies and neighborhoods of these points, but exactly at these points and nowhere else. Yeah, so I don't know. It's just a comment. Maybe you can look into it or comment on it if you already thought about that.
Oh, thank you very much for this comment. Could you please at some point somehow send me an email with this reference?
Oh, yeah, sure, no problem.
What's your name?
Benjamin Bode.
Thank you.
Okay, any more question or comment? You?
Hello, Steph. Thank you very much for your nice talk. So can you give any information about bounds for the polynomial in terms of the graph, for the degree of the polynomial in terms of the information given by the graph?
I don't know. No, I don't know this because it's not effective, this construction. So, but maybe it's possible. I didn't think of it yet.
Yeah. Well, I suppose that your graph is, in general, you try to associate to these vertical tangencies a non-degenerate singularity, right?
Yes.
Yeah. Well, I don't know, but it's a natural question to see whether we can have some estimating of the degree, right?
Thank you for the question. I will think about it.
Okay, thank you.
Any other comment or question? I would like, I will have maybe a naive question. It's in the same line as Sidinya asks to you, because at least in the first part of your work, it seems like you are applying cylindric decomposition theorem to your real algebraic set. So there you construct this combinatorial object in between the 1 and 0 dimensional cylinders and the 2-dimensional one, which is your algebraic set. So it could be maybe interesting, I don't know, to apply the same ideas for general compact semi-algebraic set or either non-compact semi-algebraic set. I'm thinking in particular to real algebraic domains with singularities, and then maybe you can label your Poincaré-Rive graph, with, I don't know, with multiplicities at some point or something who will control the kind of singularities you are getting. I think this is in the same line as Sidinya as you. Have you been thinking about that?
It's an interesting question I haven't thought about yet. So you mean that the boundary could have singularities, right?
Yeah, or either just consider a general semi-algebraic set.
So the idea, that's why, so in most generality, it would be these domains of finite type, but indeed, there we don't care about the singularities. But it would be interesting to enrich the graph and to think about this kind of, this made me think about this talk from previous days where we had some labelings with some stars where we had, just I'll tell you, by Professor Costa, that had, maybe it's not the same idea that you meant, but.
Okay, because we both know that Patrick likes labeled graph. Isn't it?
Indeed.
Okay, thank you very much.
Thank
So
you.
let's thank the speaker again, please. And before going to lunch, I have two announcements to do. So at the end of the day, after Mark Spiakowski's talk, there will be they will pass a small video here with some photos from the event, so summarizing the event of this Congress. And this is the first announcement. The second one is that I'm using my position of power as chairman to do some propaganda about this workshop we are organizing in Madrid late October. So as you know, we were together with Pablo Portilla and Patricia Almiron, we were organizing an online seminar for young singularities. So now we got some money and we are organizing an international workshop with 3 courses about current topics in singularity theory, and also several talks given by senior and young researchers. So please, if you are interested, this is a hybrid event. Just type WorkSing in Google and you will go to the webpage. So thank you very much and good luck.